In the previous lecture, we derived an equation that gives us the pressure within a fluid when the density of that fluid is constant. Now, what happens when the density is not constant? Well, we can't use that equation. We have to use a different equation. And in this lecture, we're going to derive the general form of the pressure equation that will give us the pressure within the fluid regardless of whether or not the density is constant. So let's begin with the following diagram. Let's suppose we have a certain container and we fill that container with a fluid. Now the level, the surface of that fluid is given by this blue line. And everything below that blue line actually contains our fluid. So this entire volume contains the fluid. Now, how exactly are we going to derive this equation, the pressure equation, for pressure inside a fluid when the density is not constant? Well, we're going to use calculus. And to begin, we're going to examine this fluid region. Let's suppose that within the fluid, we choose a small flat volume of fluid with an infinitely small distance dy and an area of A, so given by the letter A. So we want to find the pressure inside the fluid a certain height of y above the bottom of the container. So let's suppose this is the bottom of the container and this distance y is some arbitrary distance, and we want to calculate the pressure at this distance y above the bottom of our container. So we begin by examining the following small volume of fluid with an infinitely small thickness, dy. So we can consider dy as being the height of our infinitely small volume of fluid. Now to begin, let's look at all the forces acting on our small volume. We have three forces altogether. The first force is created by the fluid found below our object, below our small volume, and it's given by this vector 1. So 1 is simply P times A, where P is the pressure below and A is the area of the face, the bottom face of our shape. Now, what about force number 2? Well, force number 2 is simply a result of the fluid that is found right above our small volume. And force number 2 is given by the following equation. So we take the sum of the pressure from the bottom, and this infinitely small change in pressure due to the distance dy. So P plus dP multiplied by A gives us the force due to our fluid acting on the face right above our object. So these A's are exactly the same because the two faces, the top and the bottom face, have exactly the same area. Now the third force acting on our small volume of fluid is the force of gravity. And this force is infinitely small because the mass we're considering is also infinitely small. So the force 3, which points in the same direction as force 2, is simply dFg, where Fg is our force due to gravity. Now, we make the assumption that our fluid is stationary, it's not moving, and that means this chosen volume of fluid is also not moving. It's in static equilibrium. And so that means all the forces acting on the volume of fluid along the y-axis must sum up to 0. So we choose going up to be positive and down to be negative, and we get the following result. So the force, pressure times A, which is the force due to the fluid below the object, minus the force due to the fluid above the object, minus the force of gravity. Now notice the force of gravity is simply m times g. So we have infinitely small change in mass multiplied by the gravitational constant g. And next, we simply distribute our A to both of these variables. And we get PA minus PA. So we see that these two quantities will eventually cancel out. Minus dP times A minus our density times infinitely small change in volume. And this simply comes from the fact that mass is equal to the density of the object multiplied by the volume we're considering. So the volume we're considering is simply dV, and the density is given by the Greek symbol rho. So mass has been replaced with this quantity. So let's cancel these terms out, and let's recall that volume of this object is simply its height multiplied by the area. The area we said is A, and the height is dy. So this dV becomes our A times dy. And we take this and we bring it to the other side, and we cancel these terms out, and we get that A multiplied by dP equals negative the density times A times G times dy. Now A's appear on both sides. We can cross those out, and we get dP, our infinitely small change in pressure at the bottom of our container, is equal to negative the density times G times dy. So if we take dy and bring it to the left side, we get the following result. So the ratio of infinitely small change in pressure and infinitely small change in distance and height is equal to negative the gravitational constant G multiplied by our density. Now, this is the pressure equation that gives us the pressure within the fluid, and it tells us that the pressure within the fluid varies with respect to height. And the negative sign simply means that our pressure increases as the depth increases. As we go further down, the pressure increases. Now, if we take this equation and take the integral of both sides between some 2 points, we get the following result. So, the integral of dP from P1 to P2, where P1 is the initial pressure and P2 is the final pressure, is equal to negative of the integral of the product of these quantities from y1 to y2, where y1 is the initial position and y2 is the final position. Now, as long as we assume that our density is not constant, we can only integrate the left side. And the integral of the left side simply becomes P2 minus P1. So the change in pressure when we go a certain distance is equal to negative of this integral. And this is our general pressure equation that gives us the pressure or the change in pressure within a fluid when an object moves a certain distance within that fluid. Now, this equation once again assumes that our density is not constant. Now, in fact, we can use this general form of our pressure equation to find the equation for pressure when the density is constant. In other words, we can derive the equation we spoke about in the previous lecture. So if we assume that the density is constant, that it's uniform, we can integrate the right side, and we get the following result. We get that the difference in our pressure, P2 minus P1, is equal to, well, we have our product of the density, which is constant, times the gravitational constant G multiplied by y2 minus y1. So this is simply our change in displacement within our fluid. And this is the equation we spoke of in the previous lecture. Now, let's suppose we take the following container and we open up the top of our container so that our fluid inside the container is exposed to the atmosphere. Now, what will be the pressure of an object found on the surface of the fluid? Well, it's no longer zero because the atmosphere is in fact a fluid in itself. And that means the pressure at the surface of the fluid will be the pressure of the atmosphere, the pressure as a result of the atmosphere that is found above our fluid. So, from this equation, we can derive the following equation that gives us the pressure inside a fluid when the surface of the fluid is exposed to the atmosphere. So the pressure inside the fluid is equal to the pressure due to the atmosphere, P naught, plus the pressure that is a result of the volume found above the object inside the fluid.